Have you ever wondered why Einstein was so smart and seen as like such a visionary and really like the face of science? Like if you Google physics or science, you'll probably get a picture of Einstein pretty quickly. So let's talk about what Einstein discovered. So the main thing that Einstein's kind of famous for is the discovery of relativity. He wasn't the one who completely came up with the idea, but he furthered it a lot. The idea of relativity did already exist before him. There were some experiments in like the late 1800s that were kind of talking about relativity, and Einstein kind of furthered those a bit more in the early 1900s. So we're talking about relativity. What is relativity? So relativity is pretty much when things can change depending on your point of view. That probably sounds quite vague, and I'll give some examples and things so that you can kind of understand that. This is especially true when things are moving very, very fast. So when we're talking about things traveling like the speed of light, we see physics and like our perception of things get a bit weird. So yeah, and also the same for things when they're really heavy, like things like around black holes, or like, close to a sun or a galaxy or something. Like, again, the laws of physics and our perceptions can get very strange. I put a warning here, kind of a joke, kind of not a joke. This may break your brain. We're going to look at things in a different way, so probably ways that you've never imagined things. So if you're struggling to understand something, don't worry. I'm trying to keep it like as simple and clear as possible. But yeah, relativity can take some time just to kind of think about and get your head wrapped around the ideas and things. Okay, so let's start with an example. Let me get a paintbrush. This will make things a bit easier. Let's do it in yellow. Is that working? Yeah, cool. So imagine, right, I'm standing still. I'm standing like here, okay, and I throw an apple in the air. How does the apple move? This isn't a trick question. If I draw my apple, it's going to go up, and then it's going to come back down. So, I throw it up in the air, it's going to go up, come down. That's what I see. That's what you see. The apple goes up and down. Okay, now imagine I'm moving. So imagine I'm standing on a train, okay? A lot of these examples kind of involve trains. I guess Einstein and people around this time really like trains. My train is not the best. Okay, so imagine I'm on a train and it's passing through a train station. And this is you. You're standing in the train station, watching the train go by. Yeah, there we go, right you. And again, I throw my apple in the air. How does the apple move? So from my point of view, I throw the apple in the air, the apple goes up and it comes back down, okay? Exactly the same as when I was standing still. Now to you, it's going to be a bit different. So because you're watching the train as it's kind of moving in through the train station. So let's just draw this over here just a little bit easier. Instead of it going up and down, what you're going to see is you're going to see that move in an arc. Because as the apple's going up, the train's also moving sideways. I don't see that because I'm moving with the train. So from my point of view, everything is moving. But from your point of view, you're seeing everything in my point of view moving. Okay? So this is what you'll see instead. And so the faster the train's moving, the longer that arc is going to be. And the slower the train is moving, the shorter that arc is going to be, and the more it's going to look like moving just up and down. So, and again, this gets more and more extreme as things get faster and faster. So, how do I put away my pen? Yeah. So here's kind of our first rule: is that sizes can change, depending on how fast things are moving. So just want to kind of talk about a quick definition of what is space-time. You've probably heard this in like science fiction movies. People talk about it a lot of like space-time. They don't just talk about space, they don't talk about time, they talk about it together. So this was one of Einstein's big discoveries, is he was working on some equations for space and trying to look at things, how they work on the big scales. Again, like talking about like galaxies and the universe as like a whole kind of thing. And he realized his equations worked better if he linked space and time together. So this was it's called the cosmological constant. I'm not going to go into too much detail because it's quite a complicated thing, maybe in another video. But this was his kind of like big discovery as well. And the main reason for this is space is not the same as it was in the past, or it won't be the same now as it will be in the future. And what kind of came with that is he realized that the universe is also expanding, so he discovered this in 1917, and a guy called Sol Perlmutter in 1998 worked with a team of others to prove that this was actually true, that the universe is expanding. So it took us like 80 years to actually prove Einstein right. So that's kind of where the term space-time kind of comes from. So picture this. Let's try and put this into like a bit more a way we can understand of how space-time kind of works. Okay, imagine a piece of fabric laid out flat on a table, and this is our space-time. Okay, so you've got it all just kind of stretching out. Then imagine we place some marbles or some balls on the fabric, and these can be different sizes, they can be the same sizes, it doesn't really matter. But what you'll see is where the balls are placed on the fabric will dip slightly. And this is what happens with planets and stars, is they warp space and time. So we don't really notice this because things like in our daily lives, we're around the Earth isn't really that heavy in the grand scheme of things. To us, the Earth is very heavy. But again, you think of things like black holes or even the sun, these sizes get bigger and bigger. So the bigger it is and the denser it is, the more it's going to kind of cause this dimple on the fabric. So everything does have an effect on space-time, even you. But we're our weights are so small that we don't really have that much of an effect. And so what I was kind of getting at here is, so what happens is when you're around things that are heavier, because they have this big dimple effect on space and time, you actually experience time differently. So what happens is when you experience a lot of gravity, this makes time move slower from the outside, from your perspective. So again, think about the train going through the train station. If you're on the train, so in this example, the train would be experiencing a lot of gravity, say being near a black hole. Time would move the same and everything kind of seems normal. But if you're outside, things get a bit weirder. And so from the outside perspective, time moves slower. So you might have seen the movie Interstellar. This actually does a really good job of explaining time dilation. It's one of the few movies I've seen to do this really well, or even attempt to try and explain time dilation. So in Interstellar, they land on a planet and they realize that time is moving a lot faster on the planet than it is compared with everything else, because they're close to this black hole. So again, when they're on the planet, time travels normally, but they leave one of their crew behind and doesn't land on the planet. And this guy experiences more time than they do. So again, this is where things get a bit mind-bending. Put this in more kind of normal terms. So astronauts on the International Space Station do experience this. It's much, much smaller scales, but they do experience this. So over 12 months on the International Space Station, an astronaut will get 0.01 seconds less than if they stayed on Earth. So it's not that much difference, but it does add up. So yeah. So here again, to try and put this into context a bit more for you. So I have a question for you. This is called the twin paradox. So in Star Wars, right, you've got Luke and Leia who are twins. Which one of them is older? So this isn't a trick question. It's not oh wait, hang on, in the third movie, which one was born first? Which one did they name first? Oh, I can't remember. There is an answer to this. So the answer is Leia would actually be younger than Luke. So Leia is a princess. She'd be traveling all over the galaxy, going to parties and stuff like that. When she's traveling fast on her ship, she would be experiencing extreme gravity, because in Star Wars we see they travel at pretty much light speed. Whereas Luke is in a poor family. He stays on the same planet his entire life. He barely travels until the movie starts. So what that means is, because Leia's traveling faster, her time would move. She would experience less time than Luke would experience. And so what that means is Leia would actually be younger than Luke. I don't know how much. You'd have to work out how much Leia has traveled. And I think people have tried to guess, but it would be probably of the order of months or days. You're not talking years or anything like that. So this is our second rule. So we've got sizes can change and time can change depending on how much gravity you experience. So again, this, as I said, relativity gets very weird. And then, of course, Einstein's most famous thing, again, look up science and you will see the famous E equals mc squared equation, which is the most famous equation in science, and it's what links energy and the mass of an object, so kind of like how heavy it is. Except this equation is wrong. There's actually an extra part to this equation that doesn't get shown. So the actual equation is E equals gamma mc squared. Don't know why this gets left out, but it does. There's some complicated maths you can do and the gamma kind of like disappears, so it might be because of that, just to simplify it. But yeah, the real equation has this gamma in it, which is a Greek letter. I won't go into what gamma is too much, but you can pretty much think of it as the same as the speed. So what that means is if gamma is bigger, so our gamma term here is bigger, what that means is then the E must get bigger to balance out the equation. Because when you have an equation, if one side gets bigger, the other side must get bigger too. So what that means is, as something moves faster, you need more energy. And so this is what the equation kind of means is that things can't move faster than the speed of light, because the speed of light is kind of the limit of this equation. You just need so much energy that it's almost impossible. Or you need to be so light, so you need like this m term to get smaller. So you need m to go down because gamma is going up, and so to kind of keep the E the same. So the only ones that can really travel that fast are photons of light, because they have like almost no mass. So m is basically equal to 0. And so then gamma can be very, very large. So it can be very, very fast, and the amount of energy can kind of stay the same. So anyway, I don't want to get too into the technical. It got very technical there. But yeah, that's Einstein's other big discovery, is nothing can move faster than light. So these are kind of our 3 big rules of relativity: of sizes can change, time can change, and nothing can move faster than light. There's a few other weird things of relativity that I've chosen to leave out because they just get too weird and like too mind-bending, and they're quite difficult to explain. Like, I struggle to understand them. I was never very good at relativity at uni. So it's all well and good just kind of talking about relativity, but you know, is it actually useful? The answer is yes. We use this every day of our lives. If you have a phone, you are using relativity every day of your life. So the biggest one that's using relativity is satellites. So we talked about how on the International Space Station, they experience time differently. And what that means is the clocks on the satellites need to be able to keep track of the clocks on Earth to make sure they're the same. So if you sent a clock up to the International Space Station, as we said, it would get 0.01 second less per year. So it means it would be slightly behind every year. And some of these satellites, you know, they've been up there for decades. They need to know exactly where they are, need to know exactly what time it is, you know, to be able to send our phone signals to the right place or to the computer or whatever. So they need to have really, really accurate clocks that can take into account relativity. The other one's electron microscopes that use a beam of electrons. And so again, it's moving very, very fast, like basically the speed of light. So, you know, they need to take into account relativity. The last one, you're probably not using this on a daily basis, but particle accelerators also need to take into account relativity. The way particle accelerators work is they speed up particles to almost the speed of light, smash them into each other. But again, if time and sizes are getting a bit weird when they're moving fast, they need to take into account relativity to make sure when they're trying to smash things together, they actually do hit each other. Otherwise, what's the point of firing them at each other? So anyway, yeah, that was kind of just a brief overview of relativity. I hope it didn't break your brain. I hope you could follow along and it wasn't too crazy. Relativity is quite a cool topic, I think. Again, like when you look at like some of the implications and stuff like that of, you know, like time can work differently. There's another one you can do where again, some of the sizes get weird, where if you have a train that's longer than a tunnel, so you have a really long train and a short tunnel, you can work out the speed at which the train would move. The train size would then get shorter, and it would then actually be like the same size as the tunnel. Again, that like broke my brain the first time I did that, but you know, I won't go into that today. But yeah, so relativity gets super weird. Anyway, yeah, hope you enjoyed that. If you want to see something a little bit less mind-bending, I also have a video talking about exoplanets and like, you know, everything we know about planets outside of our solar system. So feel free to give that a watch, and I will see you in the next video.